Hello, this is Gabriel Dwani. I will be showing you how to do meshing and a co-ed flow in Fluent to complete Fluids Project 1 Fall 2023. The first thing you want to do is add an analysis system. So drag and drop Fluid Flow Fluent into the workbench. Now, we want to set the geometry to 2D. In order to access this panel, you will need to right click and click on properties, and then you will have access to the properties panel. Set this to 2D because we want a 2D incompressible laminar flow. So now we open a new geometry using Design Modeler. Design Modeler is similar to SolidWorks, so it will be nice to work with. Now we click on positive C to make us look directly into the XY plane. Now we want to start our sketch, just like in SolidWorks. Because we're doing a pipe, we want to do a rectangle. Now click on the origin and drag a rectangle shape. The next thing we need to do is to dimension it. We want a vertical dimension and a horizontal dimension. These dimensions are way too big. I want my height to be 10 millimeters and my length has to be 150 times that, so 1500 millimeters. So to switch to the unit system, we just go to units and I'll change that to millimeters. Now the sketch has been finished, and now we can move on to finishing the geometry. Now we want to add a surface from sketch. So we click on that, then we add the sketch and it all, then we generate, and then we have our surface finished. This is the geometry part of the Fluent simulation done. Next, we will move on to meshing. Now, we will begin the meshing process. As you can see, there's a check mark on the geometry, which means that we are basically done with it. And now we open up meshing. Meshing is a lengthy process, and it's also one of the most important things to get right in your simulation. Now, the first thing you want to do when we're meshing is to name the selections. So, this is the top wall, so I'll name it. In order to name these, you just click on them and then right click, create new name selection. The first thing we want to do is create a new sizing. We'll click on the top wall and also the bottom wall. Then apply. To select multiple things at once, we will use control click. Now, in these settings, we change element size to number of divisions. We want 200 and this amount of divisions. We want to get rid of capture curvature and change the behavior to hard. Now the settings are done, and then we click generate and it will generate a mesh. This will take a long time, so I will return when it is done. The first meshing is done. When you click on this, you'll be able to see the mesh pattern. So the second thing we want to do is do the same thing but for the inlet and the outlet. So we insert a new sizing, we click on the inlet, and then we click on the outlet. Apply, and we also want to change the number of divisions to 50. Do the same thing with getting rid of capture curvature and setting the behavior to soft. And then we click generate, and then it will generate the mesh. This will also take a long time, so I'll be back when this finishes. The second meshing is done, so you can see the result of that on these edges right here. So the final thing we have to do is to do the face mesh. This is really simple. You just click face mesh, click on the geometry, apply. You don't have to change any of these settings. Then you click generate, and this will be done now. Okay, so the meshing is now done, and we can move on. So now we just click mesh, update, and then this will change into a check mark. Now I'll show how to do the co-ed flow. Because we're doing multiple simulations, it's nice to duplicate these systems so you don't have to do the meshing over and over again. So now we're going to go into the setup by double clicking, and this will open Fluent. Now go click double precision to make your stuff twice as precise. And then Fluent will be starting up. So as you can see, our mesh is here. So we want to do our setup. So this is the model we're using. Because we want a laminar model, we just click it and then change it. Now we want to go into results, click on the residuals and lower the residuals, and this just gives the criteria for convergence. Lowering these will make it more accurate. Now we want to set up our materials. For the fluid, we want air or any other material, it doesn't matter. For this, I changed my density to 1 kilogram per meter cubed, and the viscosity to attain a laminar flow, I set it to this value. This is Editing Gabriel. I forgot to click the button that says create/edit. If you don't do that, it's not going to apply any of the changes. You see me fix this later on in the video, but just a heads up, always click create/edit to save your changes if you don't want to mess up like me. So, to get a laminar flow, you want to make sure that your Reynolds number is below 2500. And that requires multiplying the viscosity. You have to use density, velocity, hydraulic diameter, and viscosity. Remember, in this case, the hydraulic diameter is 10 millimeters because that's the diameter of this pipe. And so, what you want to do when you do this project is to make sure that the inlet velocity is small enough so that you have a laminar flow. And for this case, An inlet velocity of 8 meters per second is enough to guarantee laminar flow. Here we're setting the boundary conditions for the thing to solve. And now we go to the outlet, and all we want to do here is to prevent the reverse flow. Now the walls for a Poisson flow should be stationary, and they default to that. So it's a stationary wall with a no slip condition. It's the same for the top wall. This will always be correct by default, so you don't need to worry about it. The next thing you have to do is go to reference values. Now we're going to compute from the inlet, and that'll put in all the values we want. And this viscosity is wrong, so we're going to go to air and change it. It seems like I forgot to click change / create. Now this should be correct now. Yep. The viscosity is what I set it to. The density is correct. So now we want to go into solution and initialize this. Click initialize, it'll do 10 iterations, and then we go run the calculation. Let's do 200 iterations, and then we calculate. So it's done iterating, and we have successfully ran the simulation. So now we're going to quit. It's writing the results. We're going to go back to Workbench. Now we open up the results tab. So the mesh is there. We want to see how the velocity changes. So we're going to insert a velocity contour. So we're going to select symmetry 1 because that will give you this entire thing. We're going to look at the velocity u. Now we're going to set the number of contours to whatever we want. We're going to choose 11 because that'll make this run very fast. So if I can get this to align correctly, you can see that at the start it's slower, and it speeds up because of the favorable pressure gradient. But because this is very low resolution, we want to use a higher number of contours, and so we'll use 250, and that'll increase the resolution of these contours. So now you can see that these colors are much prettier. It's a nicer gradual transition, and it still shows the same results. We first have a slower flow, but due to the favorable pressure gradient, we have an increase in the velocity. You can see that this legend isn't very pretty, so we can change the way it looks. If we go to render, now view, this velocity contour. Oh yeah, the default legend view. So we're gonna put this horizontal, and now we're gonna change it to be a fixed, and now it looks better now. The other thing that we have to do is get the velocity vectors. So let's insert velocity vectors. Now let's put these vectors at the symmetry 1, and we'll have to see variable velocity, that's correct. So let's make these velocity contours invisible. Alright. Now we can zoom in and see the velocity vectors. So the way they look right now is really ugly. So let's use an arrow 3D and reduce the sample size to something very small, like this. Now everything should look better. So now you can see that at the center the velocity is greatest, and near the walls it's 0 because of the no slip condition. And so you can tell as we move further back towards the beginning of the flow, they start getting more orange because they're not as fast. It's fastest at the end because of the favorable pressure gradient. So this is what it looks like at the beginning. Oops. So you can tell that the velocity gradient isn't that significant at the beginning. But as you go on, it gets much more significant because the center becomes very high speed, and then the outer parts that are away from the center are lower speed. This is what we expect because of the no slip condition. There is no shear at the center. That's because it reaches the maximum velocity. So if you want to sketch the velocity profile at different positions, we can add lines, and we can use that to give us information. So first we want to add lines, and so let's call this the midline. 2 points and point 1. This is the x, and let's put this at the halfway point because it's the midline. These sliders show you, is a nice way to show you how much you have. This is working in meters, so 1500 millimeters is 1.5 meters, so we have to do half of that. Set this the same because this has to be the same x, and now let's just move this slider all the way so we reach the top. And so now we're good. Apply this, and now we need to do another one, but for the end. So let's call this the end line. And now this should be near the end, but let's make this so we don't have any errors by having it directly on the end. So now we're good. Now we can add chart of the velocity profiles. So we want the midline, and the location is going to be the midline. The x-axis is going to be the velocity u. The y-axis is going to be the y. Now we can apply this and it'll graph that. Now we want to add another data series. This time it'll be the end line. Location will be the end line. Change the x-axis to velocity u. This is already set correctly. Now we can see that the end line has a stronger velocity profile, has a larger velocity than the midline. If we want to increase the resolution, we'll increase the samples. Now it's smoother. Let's do the same for the midline. Increase the number of samples. Now it's smoother. Now let's look at the developing flow. And to do this, we'll just add another line. So let's say this is developing. Let's put this right at the very beginning. Let's say this is 0.1, 0.1, 100 samples. And now we're going to add it to the chart. And now, let's see. You can see that the velocity profile in the developing region is different from the velocity profile in the developed region. Very interesting. Now, in order to determine the place where it reaches the maximum, we're going to need to export data into Excel. Or this is pretty obvious because it's a Poisson flow, and obviously the velocity maximum is going to be the halfway point, but I'll just show it to demonstrate how we do it. So we export. So now we have these. So let's look at the end line. Then we export it. And it don't. Okay, this is good. So we have to select the variables we want to look at. Velocity U. Control click Y as well. Now we should be good. Now let's export this to a CSV. Save it. Overwrite this. Okay, so here we figured out what the max here is. So we have velocity U. So let's figure out what the max is. So get maximum of this. And this is what the max is. Let's make it more accurate. 11.97, and that's basically what it looked like in the visual stuff. And so location of max velocity. I'm going to quickly search up how to do this because I forgot. Oops. Okay, so the way you find the location of the maximum velocity is, instead of you listening to me mess up how that Excel equation works, I'll just explain it to you in editing Gabriel mode. So basically you have this match function. We pass in as the first parameter the maximum velocity. For the second parameter, we pass in all of the velocities we have. It goes through that list of velocities and it finds the index I that the maximum velocity occurs at. And then we pass that index I into the index function, and we also pass in the list of heights, and then it's gonna give us the height associated with that index value. And that is how this equation works. So this is basically the center, because this is in millimeters. Meters, I mean, to convert that to millimeters, it's 4.95 millimeters, which is basically the center. So now that we have finished simulating the co-ed flow, we can actually duplicate this. And so the mesh is already done, and we have also gotten a format for the solution. So all you would need to do is change the setup and run the simulation again in Fluent, and then you should get the new results. So what we did in the results is we created the line, the chart, the contours, the vectors. The only thing we would have to repeat in that part is exporting to a CSV and finding the max velocity and the location of the max velocity. But we don't have to copy the meshing or the results part. All we have to do is go into the setup and change the boundary conditions. To simulate the co-op flow, we're going to need to set the inlet velocity to 0 and have the top plate be moving, or it could be the bottom plate, it doesn't matter. However, in this case, we'll need to change the viscosity to something greater. In this case, I used 10 to the -3 for the viscosity. That gave me a linear velocity profile. So the way that we set up the boundary conditions is we go to inlet, and we right click it, go to type, and set it as a pressure inlet. And then we click in, and the only thing we want to do here is set this to prevent reverse flow. Now we go to the walls, click the top wall, and we should set it to a moving wall with a no slip condition. For this one, I use the speed of 3 meters per second. And that's done. Remember to go into reference values and set compute from inlet. Now we go into initialization, initialize, and then we run the calculation. Now the calculation is complete, and when we go into the post-processing, update the results. It took a long time to update the results, so I spared you the wait. So, as you can see, the velocity is 0 at the bottom wall, and it's 3 meters per second at the top wall because of the no slip condition. This is what the vectors look like. It shows the same thing as the contours, and now we look at the velocity profiles, and it's a straight line as you would expect. And the developing flow, it's the straight line as well. Each of the profiles is on top of each other. This is what we would expect for a co-op flow. Now I will be demonstrating how to do the hybrid flow. So for air, I use the viscosity of 10 to the -4 Pascal seconds, and then for the boundary conditions, we set the inlet to be a velocity inlet instead of a pressure inlet, and for this one, the velocity magnitude was set to 8 meters per second. For the top wall, it was a moving wall with a speed of 3 meters per second with a no slip condition. The bottom wall is stationary with a no slip condition, and the outlet is still a pressure outlet that prevents the reverse flow. We set it to compute from the inlet and run the calculations as usual. These are the results of the calculations. As you can see, the velocity is highest near the center, but it's not exactly the center, and at the top wall the velocity is greater than at the bottom wall because the top wall is moving and the fluid abides by the no slip condition. This is what the velocity vectors look like, and this is what the velocity contours look like. So as you can see, the velocity contours very clearly show that the velocity at the top wall is greater than the velocity at the bottom wall due to the no slip condition. This is what the chart looks like. So, as you can see, there's a difference between the developing and the developed flow, but in this case, you can see that the location of maximum velocity isn't exactly at the midpoint. This is because the moving top wall is shifting the location of maximum velocity upwards. And to figure out where that location of maximum velocity is, we will need to use Excel again. So we export the data to Excel as the combined one, overwrite, and now we're going to be determining what the max velocities are. So max velocity, location of max. So the max velocity, use the max function, drag it over to our data. It's this value, and now get location of the max. We use index, and this is the array where it should be at. And now we get the location of maximum velocity. As you can see, it's 0.0054. Now we can copy this. And let's change these numbers so that they become more readable to us. So, as you can see, the max velocity at the developed region in the midline and end line is basically the same, and the locations are the same. But the location is not the middle, it has been shifted up slightly. And for the developing flow, the location of the max velocity is downwards. That's interesting, I wasn't expecting that.